write there your name and surname. That's a requirement from organizers.
Só que não sei.
Eu мог написать количество секунд, потому что там что-то нельзя клик,
Да, можно. Расчет вчера проходил этот имплисит, и, видимо, он у него готовый темплейт был.
Я думаю, может, и заранее знать.
Тогда я расчет проходил, да, типа.
Заранее везу еще до этого. Потому что мы когда приходили, мы заранее имплисит сегменты себе должны поставить на чуть-чуть.
Sabah üçün ümumləri email göndərim yenə hansı otaqda olacaq? Təkrar göndərmiş olacaq. Göndərim. Gün axşam göndərərəm. Video yəni hansı otaqlarını təsdiq edəcək. So sometimes we change, so it doesn't mean that this room will be for capital. So we'll replace this room with this room or another. So thank you very much. Let's start.
Okay, let's start our tutorial. Let's start from the problem A. Problem A was about the problem was about we need to find Centroid. We need to find Centroid in the tree, and most of participants solved the problem, and that means we can go to the next question. The next question was in lecture. There we need to find the number of paths that have length equal to k. And in the contest page, if you go to the contest page, there in comments I left the link to the code that was in the lecture. I checked the code, and the code is working. Okay, let's go to the problem C. Problem C was a harder version of problem B, where we need to find the number of paths that have distance between k1 and k2. We have 3 and 2 variables, k1 and k2. We need to find number of pairs of vertices that dist uv will be lie on that segment. Okay, that's not many hard to find this. Okay, how we can find how we can solve the problem? To solve the problem, what we need to do? We need do the centroid decomposition, And in Centroid decomposition, we have Centroid and other subtrees. And okay, we need and we calculate the distance to the every vertex. Let's call that dv. dv would be distance to the vertex v. Okay. How we can to calculate that number of pairs, we need to use maybe some data structure. We can use segment tree. How we can do this? There will be our segment tree, and that will be our segment tree, and we need to add every vertex in first subtree to the. We need to add every vertex in first subtree to the segment tree. We need to update position for every vertex v. We need to update position dv to +1. We need to add +1, and after that we look at the second subtree, and for every vertex we need to calculate. We need to calculate how many vertices from first subtree that dv plus du will be lie on that segment. Okay, we have two requirements. That first requirement that k1 that k1 v plus du, and because we know vertex v and we need to calculate, we need to count how many vertices u that lie in the first subtree, and dv plus du will be at least k1. Because we know v, we know what value should du be. Du need to be at least k1 minus dv. That will be the first requirement. And the second requirement will be that right that way, k2 dv plus du need to be at most k2. We know v, and that means that du should be at most k2 minus dv. Okay, and we see that du should lie on segment from k1 minus dv to the k2 minus dv. And we can just get on, because that's the segment tree, we just can call get function and add to the answer number of vertices that lie on the segment from k1 minus dv to k2 minus dv. We just add to the answer number of vertices that lie on that segment, and after that, after we calculate the answer for every vertex, we need to add every vertex in that subtree to the segment tree. That means for every subtree, we need to, first of all, we need to calculate how many vertices that they can match with our vertex, and we need to do that for every vertex in that subtree. After that, we add every vertex in that subtree to the segment tree. After that, we have the answer, and that will be work and log squared, because Centroid decomposition works and log, and we use segment tree, and segment tree will work log, and finally we have n log squared. That is solution. Okay. Do you have questions code. Yes.
Is it possible to solve it without segment tree just by using prefix sum?
Yes.
Prefix sum
I
is
showed
problematic.
in the lecture two methods. We use two methods that we use when we calculate the answer. That was the second method when we look at the subtree, calculate the answer for that subtree, and add this subtree for some data structure. That was the second method. First method was when we take all vertices, sort them, calculate something, and but we need to subtract some pairs that lie on one subtree. Yes, and for every subtree we subtract the pairs that lie on that subtree. Yes, and that was the first method. You can use first method in that problem. That is not important. You can use method you want.
But actually, can't we use the second one where we just like saving the new elements, we adding them to the set, and then finding using lower bound? Like how many elements are less than
Set,
k minus something in the set?
You mean set? I think simple set cannot do it.
Like unordered.
Unordered set.
No, not unordered,
Ordered
multiple,
set can,
multiple.
yes, we can do it. That will work. You can use that set. Ну, вместо дерева описано.
Instead of segment tree, we can use ordered set,
No, not ordered, multiset.
multiset.
Oh yes, multiset. You can change the segment tree to the multiset. Yeah, you can do it. That solution will be maybe easy. Easy. Yes, that solution will be easier than segment tree. I don't like write segment tree when I solve the problems to the centroid decomposition, because code of centroid decomposition is quite big, and I like use sorting, lower bounds, sets. That is more easily than write segment tree. Yeah. Okay.
No,
Do you have questions? Okay, we can go to the next problem. Next problem was okay. Go down. Okay. Next problem was problem D. Okay, go to the problem D.
Also, I'm sorry, before moving to the other question, is problem C similar as problem G?
G.
Yes, close vertices.
Oh, G.
Kind of different.
I think kind of different, because many problems on centroid decomposition there looks similar, but that's different. That's their different solution. I use. Okay, let's look to the problem D. Problem D was more easy than problem C. There in problem D, what we need to do? We need to assign the ranks for every officer, and in that problem, what we need to do? In 3, what we have. Okay. In that problem, how we can solve the problem? We just need to find the centroid of that tree and assign to the centroid C letter A. We assign to the centroid letter A, and when we go to the subtrees, we assign to the centroid of that subtree letter B, and after that letter C, and we go on and go on. Because we in Centroid decomposition we have log levels, we use at most log letters, and it's okay to solve that problem. That means impossible. That means that for every tree where that means for every tree where n is not big, we can always we can assign to the every vertex letters in that for that input. Okay. Do you have questions about problem D? Okay. Let's go to the problems. Let's go to the problem A. Oh, E. Okay. In problem E, what we need to calculate? In that problem, we have tree, and for every vertex we have his value. Every vertex has some value, and distance in that problem that is not sum. That is XOR of all values that lies on the root. That means this VU, if pass from VU will be if pass will be like P1, P2, pass from V to U will be P1, P2, and Pk. That means we need to. That means that this VU will be equal to the AP1 XOR AP2. Oh, AP2 XOR and like this. To find the distance, we need to calculate XOR on the pass. In that problem, we need to calculate sum of distance for every pair of vertices. Okay, how we can do this? If we know centroid decomposition, that is very not hard problem. Okay, we have centroid, and we need to calculate sum of pass that goes through the centroid. Okay, how we can do this? Let's use the second method I told you on the lecture. We add every value in the first subtree to some data structure, and after that we need to for second subtree we need to calculate answer for every v in the second subtree. We need to calculate the answer for every u that lies in the first subtree. How we can do this? Okay, we calculate dv, that will be distance from centroid to the that vertex. That means we need to calculate sum of dv XOR du. Okay. In XOR problems, what we need to do? We need to look for every bit independently. Let's look force for every bit, and we fix some bit. Let's look to the bit I. How many times bit I will be added to the answer? And we need to look. Because because we fix the vertex v and the bit I, we need to calculate how many times for vertex v i's bit will be added to the answer. That means we need to know in what case dv XOR du have i's bit. dv XOR du has i's bit when their i's bit is different. That means we need to, our data structure will be some array cnt, cnt I1 and cnt I0. What is that? Cnt I1, that means how many vertices in first subtree has i's bit, that i's bit equal to 1. And cnt I0, that means how many vertices in first subtree that their i's bit equal to 0. We need to store that values for every bit I. Okay. Then after we store that CNT arrays, we can calculate our answer very easily. We need for fixed v and for fixed I. We just need to look. We need to look to the I speed of vertex v. Let's assume that our I speed of dv will be equal to the b. B is yes. B will be I speed of dv, and we just need to add to the answer ans plus cnt I1 minus b, because I said that dv plus du, I speed dv XOR du will be added to the answer when their I speed will be different. And we just need to add to the answer cnt I1 minus b multiplied by 2 in 2 in i's power. Okay, and it's that. After we calculate answer for second subtree, we just add every value to the CNT arrays and do that to the third subtree and do the next subtrees. And time of complexity of our algorithm will be n log n squared, because we need to go through the old bits, and we have log bits, and that will be work n log squared. I think it's all. Do you have questions? Okay. Oh, that was problem E. It was problem E. Okay, go to the next question. Oh, yes. Go to the next question. Next. Hold on. Problem F. Okay. In problem F, we have 3, and sorry. In problem F, we have some 3. And we want what we need to do? We need to learn how to quickly execute queries. We have two types of queries. First query, we need to paint some node to the red, and second type of query. Okay. Okay. Initially, our first vertex will be colored to the red, and other vertex will be blue. And we need to execute two type of queries. First, we need to paint some node. Paint node in red. And second type of query, we need to calculate. We need to find the shortest distance to the. Okay, there give us some vertex v, and we need to find the distance to the shortest distance to the red vertex. Okay. From node from the node. Okay, that is the type of problems that where we need to store our centroid decomposition. In previous problems, we don't need to store centroid decomposition. We need to calculate some answer and forget about our centroid decomposition. But in that problem, previous problems was like offline problems when we need to calculate something. But in that type of problems, that problems called online, when we need to execute some queries, we can use centroid decomposition for those problems. How we can do this? We need to store our centroid decomposition. Okay, let's forget about our first type of query, and look to the second type of query. Let's solve the next problem. We have tree and some vertices colored to the red. And for every vertex, we need to find the nearest red. We need to find the nearest red vertex with centroid decomposition. With centroid decomposition, that is not hard problem. What we can do? We have centroid and some subtrees. That centroid controls all paths that goes through the C, and we can store for that centroid nearest red. We can store for that centroid nearest red vertex. It can be there. Let's let's call this array mn. No, it can be d. Assume that dv will be shortest distance shortest distance to the centroid. Okay, let's calculate shortest distance for that for our centroid, shortest distance to the red vertex, and we can, for every vertex that lies in that tree, we can say that answer will be we need to store the distance. Okay. Then okay. Let's we make another variable. Not TV. Let's call just dist CV. That will be distance. Dist CV that will be just distance from C to V. From C to the vertex. And then after we calculate the shortest distance to the red vertex for our centroid, we can say that for every vertex V that lies in that tree, answer will be at most. No. Yes, answer will be at most this. We can make this and CV. And dist VC plus D. Yes. Initially, we create array ans. There will be infinities on for every position, and we can do this for every vertex. For every vertex, we say that answer will be at most distance from that vertex to the centroid, and we calculate for our centroid the shortest distance from red vertex to our centroid, and that will be right when V and our red vertex will lie on different subtrees. But when there will be both of them will be one subtree, that will not be correct, but that will not
Interrupt.
That will not interrupt to us, because we need to calculate minimum answer. And when V and when two vertex will be one subtree, we calculate the more distance than their loss, and that will not interrupt us. And because if that was answer, we recursively calculate the right answer when we delete this centroid and go to that subtree. And because of that, we can use this method. We calculate the nearest red vertex to the centroid, and for every vertex we do this stuff. At the end, for every vertex we calculate the nearest red vertex. That was the solution of the problem when we have some red vertices in our tree and we don't have first type of query. When we just need to calculate for every vertex, we need to calculate the nearest red vertex. But if we solve the problem in this way, we can solve the original problem. Now we have update query when we need to paint the node in red, and we need to find the shortest distance to the sum node V. Okay, let's store our centroid decomposition. That means that for every let's store our centroid decomposition. That means for every centroid we need to keep shortest distance from the red vertex to our centroid, and we need to keep this for every centroid. Every vertex, some of the moment will be centroid of his own subtree, of his own tree, and we need to keep the shortest distance to the vertex when V will be centroid of his tree, and we need to store distance from every vertex to the centroid. We have keep that in vectors, and that means that sum of sizes of every vertex disk, every vector disk will be m log n. Okay, what we do when there will be first type of query, we just need to update dv for every centroid. We need to find the node v, and when we call color v to the red, we just need update to the every centroid that v lies on his tree. We need to update his value d. That there will be not more than log, because on centroid decomposition we have log levels of log levels. We just need to update log vertices, because v would lie he was have only log centroids, and we just update their value. But when we have the second type of question, we do the same stuff. We just look to centroids of vertex v, and we just we can just get minimum from for every centroid c that v lies on the subtree, that v lies on the tree of c. We just get the minimum of that value for every centroid, and there will be log centroids, and we calculate the answer. That is the solution. Okay. Do you have questions? Most of the online problems to the centroid decompositions solved in that way, and most of the centroid decomposition problems are very similar, and the solutions are very similar too. Yes. Okay, if you don't have questions, we can go to the next problem. Problem G. See? Yes, problem G. I'm surprised that nobody solved the problem G. Okay. Oh, okay. That is like two-dimension. That was like, yes, that is very. That sounds like similar to the problem C. What we have? We have tree, and we have weighted tree. That means every edge have his own weight. Every edge has his own weight, and we need to calculate how many paths. How many paths that distance of that path will be at most L. We have two variable L and W. That distance VU will be at most L, and we have another distance. First distance will be a number of edges on path from V to U, and we have second distance that will be distance that will be sum of weights of edge on the path from V to U. That this V that this W U will be at most W that given in the input. Okay.
Can we solve this using sweep line, please?
Sweep line.
Sweep line.
Centroid, but we.
Centroid uses sweep line.
Yes, the solution will be sweep line. How we do this? Okay. We have. Okay. Let's delete this tree and. Okay. We have Centroid, some trees again, and that is our. Okay. For Centroid, we have, for every vertex, we have three variables. First variable will be his distance of edge from the C. For every vertex V, we have distance dV by the edge. Distance by the edge, and we have second variable that will be distance by. Second variable will be distance by weights, dW, and the third will be that will be number of his subtree. We can call that color. Let's call that color. Color will be number of his subtree. Like every subtree has his own color. Like first subtree is yellow, second subtree is red or pink, and the third subtree will be green. Yes, we need to store three variables for every V. And okay, we need to calculate how many number of pairs VU. That first requirement will be dV plus du is at most L. dW V plus dW U will be at most big W, and their color should be different. And for every pair vertices VU, that their color is that lies on different subtrees. That means that their color will be different. For every vertex called equal U, we need to add to the answer +1. We need to calculate how many pairs. Okay, we can do this. In that problem, we just use first method on the centroid decomposition. First method of solutions. We just need to let's forget about color and let's think that we have only pairs of dV and du. let's forget about color, and we calculate how many pairs will require that two requirement will be right, and after that, for every subtree, we just subtract how many pairs of vertices that lies on the same subtree, and that two requirements will be correct. We just subtract that pairs, and it works. Okay, how we do this? We just sort. Okay, we forgot about the color. Okay, I can just. Yes, we just forgot about color. Okay, how we can solve this problem? We can use many methods. We can write two-dimensional sigma tree, but I think in that problem that we will get time limit. Sorry. Sorry.
Two-dimensional
Fenwick. I think Fenwick will get time limit too, because I unlock Coop. That is too long time. But we can just use swift line algorithm. How we do this? We do this very easily. We just need one Fenwick or segment tree, one-dimensional. We have array of indexes of vertices. Let's sort them by their weight. That means we have array of indexes. Let's call that array A. A1, A2, and AK. AK. That will be indexes of that will be array of indexes of vertices in that tree. Let's sort them by their weight, distance. That means dv A1 will be less or equal than dv A2, and like this. Okay, let's sort our vertices by their weight value, and after that, what we can do? We can do next thing. Let's fix. Let's go from for every vertex from the left to right, and let's fix some vertex AI. For that vertex, we need to calculate how many vertices in that vertices in that array can make with him a correct pair. Yes. First of all, that vertices will lie on some prefix, because for that vertex AI, he has distance. He has distance by weight d w. Oh, sorry, d w AI, and that means that if we want to calculate j's that dv that that at most w, if we want to calculate how many number of j's can get pair with him, correct pair, then that j's lies on some prefix. That means that we can use two-pointer method for keep that prefix. We just use two-pointer method for keep that prefix. Okay, we can handle that requirement, but we need to count the first requirement. First requirement by their distance. That requirement we can handle by the Fenwick tree. The solution looks like this. We add every vertex to the Fenwick. We add to the Fenwick their first distance. Okay? We add to the Fenwick their distance by edge, and when we fix some AI, when we fix AI, and we want to we want to count how many J's that their two requirements will be correct. We just keep the prefix that requirement will be correct, and that prefix of vertices will be in vertex. When we go to the next vertex, our prefix will be some vertices of that some vertex in that prefix will go out from that prefix. That means our prefix will be will go to the right or will go to the left. That means we just need to delete that vertices from the Fenwick tree. And in Fenwick tree, we just need to do two operations. First operation will be update on position, and second one we need to do get on the prefix, and that's it. That's it. Okay. Do you understand the solution? Do you have questions? No questions? Okay. Okay. We can go to the next problem. Last problem. The last problem was quite hard because. Okay, I can tell you. Let's look to the statement of the problem H. Problem was about okay. We have tree, and every vertex every edge has his own beautifulness. That will be yes. Every vertex has his own beautifulness, and for every pass that his distance will lie on the segment from L to R. Okay, for every pass from B to U, that his distance lies on segment from L to R, we need to find most beautiful pass. What is beautifulness of the pass? Let's write beautifulness of every edge on that pass. Let's imagine that will be A1, A2, and A1, A2, AK. That is, imagine that will be beautifulness of edge on the pass, that lies on the pass. And beautifulness of the pass will be median. Yes, that will be median of the sequence. What is the median? Median is we just need to sort the array and take the element that will be on the middle of that segment. If segment has even length, we just need to take if segment has k elements and we sort them, the median will be a k divided by 2. Yeah, something like that. Okay. How we can this? Okay. From for every pass that has that distance from L to M, we need to find most beautiful. We need to find most beautiful pass, and we need to out the vertices at the end of the pass. Okay, let's try to solve this problem in some way. How we can solve this problem? There we do the beautiful technique that we sort. We do binary search. We do binary search by the answer. We fix some x, and we want to know is there some is there some path that has beautifulness? Let's beautifulness will be BVU. Beautifulness BVU, that will be beautifulness of the path. We want to know is there path with the correct distance that his beautifulness will be at least x. We fixed x by binary search. We binary search x, and yes, we want to know is there some path with correct distance that has at least beautifulness x. How we can know that? Let's do the next thing. For every edge, if an edge has beautifulness b, let's we assign to him the weight 1. If his beautifulness with at least x, if his beautifulness at least x, his weight will be 1. Okay, let's write this there. At least x, then weight of this edge will be equal to 1. Else, his weight will be equal minus 1. Then, if his beautifulness is less than x, his weight will be minus 1. Yes. If beautifulness of the edge, if beautifulness of the edge will be at least x, then his weight will be 1. And else his weight will be minus 1. With that, we can easily check if beautifulness of the path will be at least x. We just need to calculate sum of weights on that path, and if sum of weights on that path will be at least 0, then that means that beautifulness of the path is at least x. And because we fixed the x by binary search, and we get and we assign to the every edge his weight 1 or -1. We need to check, is there some is there some path that that his distance will lie from L to R, from L to R, and his distance by weights will be, and his distance by weights will be at least 0. Okay. How we can do this? Let's do this with centroid decomposition, and in centroid decomposition, we have centroid, okay, and for every vertex we calculate the distance to the centroid, distance by the edge, and again distance by weights, and his color. Color means number of his subtree. That will be first subtree, that will be second, and third, and like that. Okay, and we need to know, is there some pair that their color will be different, and sum of dv will lie on the segment from L to R, and that sum of their distance by weight will be at least 0. If we find that path, we can return true or return false, because we do the binary search stuff. Yes, we do binary search stuff. We fix it some x, and with some x, we calculate for every vertex his weight, 1 or -1. Okay, and that's solution. And how fast we can make this? We can make this by very easily with segment tree, but with segment tree we solve this problem only this part with time complexity and log in square, and with the binary search it will work. And log and coup, and log coup. That is quite long. But the author of the problem says in editorial that if you write this that solution very carefully, you can get accepted. And he writes that, or if you change the segment tree to the QI with maximum, you can get more faster solution. But actually, I don't know how to do this. I don't know how to do this in linear time, because what we have centroid decomposition that works in. We have centroid decomposition that works in and log time, and we have binary search that will work one more log. That's the part of time complexity that is centroid decomposition. That is binary search, and we need to solve this problem for one centroid. We calculate for every vertex dv, dwv, and color v, and we need to calculate the answer. We need to find is there some path that their requirements will correct, will work. we need to solve this problem in a linear time. But I don't know actually, can we make this in linear time? After don't say about that. Is his solution work in linear time or n log n? Because in n log n we can use segment tree, but segment tree has a big constant. We can change segment tree with sets. We can use sliding window, and we can store set. And if we write, I think if we write this solution, we can get accepted. We just need to write this solution very carefully, and I think there are no problem with time limit if we don't use segment tree, if we use sets. But actually, yes, that is the idea of the problem. I looked to the code of many users, and I cannot find the solution in linear time. Most of them solved this. Most of them solved this problem with segment tree. You don't need to think about the solution. You just write. But some people's get accepted with sets. That is very good. That is very good solution because that solution, the code of the solution with sets will be less than the solution with some segment trees. And I cannot find the solution with linear time with quiz. With quiz that can store the maximum in linear time for sliding window. I know the technique, but I cannot solve this problem in linear time because the colors is как сказать, VPN.
Можно сказать uncomfortable просто. Можно сказать uncomfortable to write.
Colors is very there's a problem with colors because colors will need to be different for V and U. But yes, and I think about the solution when I can store the two maximums. First maximum will be the actual maximum, and the second will be second maximum, but his color of second maximum need to be different with first maximum. But
second unique maximum.
Second unique maximum, yes. But I don't know how to do this in linear time. I know how to do this with sets, but I don't know how to do this in linear time. Maybe there need to store two quiz, but it sounds very bad. Okay. Do you have questions? Okay, I can say some tip of that in the problem. When you do binary search by value, when you do binary search by value x, you can you don't need to do binary search from 1 to 10 in power 9. You can do by the values of edge of that tree. There we have n edge. That means we have n values. We can just compress them and do the binary search by the unique values. And I think that the solution will work by 2 times faster. Yes, that's all. Do you have any questions about any problem? Okay, I think I